Welcome to CE 3372, lesson 13, I believe, in the fall of 2020. And let me make a few changes on the phone call. We'll turn off the sound and go ahead and re-enable the waiting room so automatic login is disabled. And we can begin. So today's lesson, and I'm acting like I'm sharing the screen, and that's not happening yet. See, do you all need to be able to see me? Not right now, so we will spare you having to deal with that. And we will just share the actual screen. So, as I said, welcome. Let me bring up a chat menu, so if you want to talk to me that way. And modify the layout of, oh, that's right, you can't see that, so that's fine right there. All right, so the lesson for today, hope that doesn't break. Okay, good, that didn't hurt anything. I'm at our class homepage, CE 3372, section 1, and at the bottom here is the lesson 13 module. Before I start it, are there any questions regarding the current homework or the current examination? Just a reminder, the examination is due midnight tomorrow, is what I think the server is programmed. So by all means, you need to look at it sometime between now and tomorrow evening so that you have a sufficient time to be able to do it. Okay, no questions right now. Well, if something comes to mind, go ahead and feel free to enter it in the chat box, or if it's super urgent, go ahead and unmute yourself and just ask the question. So we're going to lesson 13. As we did in our last lesson, we have left pressurized pipe systems, and now we're in open channel system. And if we click on that, Blackboard is running phenomenally slow right now. I was doing some grading just before I started the video, and literally to move something took a minute. Literally to click on something, it took a minute for it to decide if it thinks it was going to respond. So this lesson is going to examine open channel flow concepts for the particular condition of normal or uniform flow, and we will explain what that is shortly. This is material you likely have had at some level of detail in your fluids class, and you also would have seen this in your hydrology class. So this is somewhat reviewish, but we will proceed with enough requisite background that if you haven't remembered it from either of those two, it should come back to you quickly. In the notes, there's some useful readings, and the ones I'd recommend you read would be this one, Open Channel Flow by Robertson, Cassidy, and Chowdhury. It's a chapter from an old textbook from the 1980s, and you know it's old because if you look at it, everything looks like it's in sepia because the paper has yellowed. And then Basic Hydraulic Principles of Open Channel Flow is a good book. It's from the National Training Center of the United States Geologic Survey. Oh, interestingly enough, it's also circa 1988. And then if you want a more traditional textbook reading, this component, Urban Stormwater Management by Ralph Werbs and Wesley James, dated 2002, is available. By all means, take the time to look at one of these three, preferably all three of them. In this particular lesson, we have data links to a couple of worksheets, and we'll visit those when we get to it, and then some spreadsheet calculators that will make the calculations that we're about to describe in the presentation. And let us begin. So choosing notes, I will choose the portable document format, and we shall begin. So the topic of today's lesson is the generic topic of open channel flow, in particular, steady normal flow. So we'll start off by reminding ourselves what's meant by the terminology open conduits. Open conduits are conduits or pathways that liquids follow, and the upper boundary of flow to the pathway is the liquid surface. And that's distinct from a pipe that's completely full as we understand it, because the upper boundary of flow at that point is the top of the pipe. The water can't get any deeper in a pipe that's already full. So that's the main difference in a sort of layman's type approach. If the water can somehow get deeper, it's an open channel. So examples of open channels that we're familiar with from our everyday lives: canals, streams, bayous, rivers, creeks, brooks running through hollers, drainage ditches, bar ditches on the side of the road, and so forth. Those are our open channels that we mentally easily associate with the concept of open channels. Sometimes we forget, but storm sewers and sanitary sewers are usually hydraulically open channels because the sewers are operated with a free surface. There is a little bit of air at the top of the pipe between the top of the water and the top of the pipe, so that if you get stuck into a sewer, you could float up on your back and get your nose up just above the water and breathe. If it's a sanitary sewer, that's not going to help you because it's going to smell bad. So just do that as a mental image. Don't try this in real life. Some parts of storm sewers and sanitary sewers are intentionally operated in full pipe mode, and in those instances, those cases, those are called surcharged pipes. Sometimes it's done on purpose, and if that's the case, that part of the system where it's a surcharge pipe is no longer an open conduit, but the rest of it will still be so. The important hydraulic principles are friction, gravitational forces that yank water downhill, and pressure forces that keep it moving and conceivably push it uphill. So we'll look at the first flow regime that's important for design, because we actually make all of our initial designs assuming that steady uniform flow is a good model of the system, and then we test that design with a proper hydraulic model. For a given discharge Q, the flow at any cross section is described by a combination of the flow depth, how deep is it? So how high is the water, mama? 6 feet high and rising. I think that was a Stevie Ray Vaughan song. The cross-sectional area at that depth, the elevation of the bottom of the channel, that handles the topographic slope that makes everything go, and the mean section velocity. These relationships between flow and depth, area and depth, wetted perimeter and depth, top width and depth are not unique. In open channels, there's 2 or 3 flow regimes that can all produce the same discharge, yet have different values of depth area, depth perimeter, depth top width. And so the knowledge of the flow type is somewhat important in the hydraulic assessment of your design. And just to refresh your memory, back in fluid mechanics, you were introduced to subcritical, critical, and supercritical flow regimes. And these play the same role in liquids that subsonic, transonic, and supersonic play in stuff that flies through the air with the greatest of ease. Most of the flows that you encounter in engineered and natural systems are usually subcritical or critical, or only barely supercritical, with the exception of flows in places like Albuquerque, the steeper parts of Montana, parts of Tennessee, where you have water that's coming off of a mountain range, and it gets a lot of energy, and it can become supercritical. So if you end up working in those parts of the world where there are supercritical flows, you'll have to refresh your memory at the time, because things behave different when they're supercritical. So we'll look at the first case, steady uniform flow. Uniform flow, also called normal flow, is flow in a channel where the flow depth does not vary along the channel. So visualize a channel. Let's say it's a rectangular channel. If you're at one location in the channel, maybe the flow is 1 foot deep, and you move a couple hundred feet downstream, and the flow is still 1 foot deep, and the channel's the same width. That would be a uniform flow situation. And uniform flow exists in real world. In natural channels, it doesn't sustain itself very long. It will usually revert to some type of subcritical. But engineered channels, we actually can engineer them on purpose to maintain uniform flow over somewhat long distances. So the Central Valley system in California, which is a series of aqueducts, is designed so that it has uniform flow for several hundred miles. And that gives them very good operational control of that water. In uniform flow, the slope of the water surface will be the same as the slope of the bottom of the channel. And in fact, a version of that is the definition of uniform flow. So let's look at a drawing about steady flow and start to learn some of the terminology. So in the presentation, there's a sketch. Looks like it's hand-drawn. It looks like my drawing, so it's quite likely I drew this at some time in the past. And there's a horizontal line at the bottom of the sketch that's labeled datum. And so all measurements of heights are measured from this datum. So this is a reference line. It's simply a elevation from which everything's measured. On the left side of the figure, there's a 1 with a circle in it indicating that this is cross-section number 1. So we're looking kind of sideways at the channel, and this is an elevation view. And over here is section number 2 on the right side of the figure. If we go to the location where section 1 is, and we measure upwards from the datum to the channel bottom is indicated by these hash lines that are next to the channel bottom line. The elevation of that point in this drawing is labeled as Z1. So the elevation to the bottom of the channel is Z1. If we continue moving upward from the bottom of the channel to the top of the water, that distance is Y1. So Y1 corresponds to the water depth in this drawing. And if we were able to move up to a hypothetical energy grade line, we would move an additional distance from the water surface up to the energy grade line, and that distance would be V1 squared over 2g. So it corresponds to the velocity head. By convention, in this drawing, the upstream section is section 1, the downstream is section 2, and we normally indicate flow direction, which is this little arrow here. And I'm a right-handed person, so almost every time I do a drawing, my flow direction is, unless I think about it, is going to be from left to right. Left-handed folks tend to draw it the other way. So if you become a forensic hydraulic engineer helping fight terrorism throughout the world, you'll be able to tell if the hydraulic terrorist is right or left-handed simply by the routine flow direction they draw in their drawings. Returning to the bottom of the channel, where we have the channel bottom indicated with the hash lines, we see this triangle here, and what that's indicating is what the slope of the channel bottom is. And the usual symbol for bottom slope is S sub 0. Or if they pronounce it like British people, it's S naught. And S naught's easy to remember. It's the stuff that comes out of your nose when you have a head cold. You have snot come out of your nose. This dashed line at the top where the cursor is moving right now is the energy grade line. It's the sum of the elevation, water depth, velocity head, and its slope is indicated by the symbol S sub F. Slope of the energy grade line, S sub F. The terminology friction slope also appears in the literature. So we have bottom slope, we have friction slope. These two stations are delta x units apart in distance, indicated by this distance dimensioning line segment at the bottom of the drawing. And in this case, delta is just indicating a change. So there's no requirement that delta x is a numerically small value. Later on, there are instances where we will assume that that's true. But delta x could be a few hundred feet in this drawing. And we can use the knowledge of that distance to work our way from a downstream location back upstream. And the change in elevation of the channel bottom from Z1 to Z2 is simply S0 times delta x. So Z1 minus Z2 equals S0 delta x. At the top of the drawing, there's a horizontal line where the cursor is moving back and forth right now. And that is the total energy line that would occur if there were no losses in the system whatsoever. And so at point number 1, the drawing assumes that we've intersected the energy grade line, and if there were no losses, the energy grade line would proceed horizontally across. But that's not the case. There's actually losses, and that's indicated by the friction slope. And so the distance between the energy at section 1 and the energy at section 2 is this distance from that horizontal line down to the energy grade line at section 2. That's called the head loss. And in this drawing, the head loss is equal to the value of the friction slope, S sub F, multiplied by the space between the two sections. And I think that pretty much beats this drawing to death. So, still reusing the drawing, the hydraulic energy at any one of the sections is the sum of the elevation head, so in this case Z2, plus the pressure head, and the depth plays the role of pressure head that we were familiar with from our earlier Bernoulli's equation, plus the velocity head. And that brings us to the total hydraulic energy at that particular section location. We can actually color the different lines and use those to explain some other things. So the water surface, which is shown here as the blue line, happens to also be coincident with the hydraulic grade line. So finding a hydraulic grade line in an open system is relatively easy. Just go look and the water's right there. There's going to be a hydraulic grade line right there. And if you're especially lucky, it'll in a real system, you'll see this blue line flowing downstream. You won't if you see a blue line flowing downstream. There's some sort of nasty chemistry going on. But we see where the water surface itself is, and that is the hydraulic grade line. The energy grade line is the hydraulic grade line plus velocity head. Now, sadly, we can't put on special goggles hooked up to our smartphone and be able to visualize energy grade lines as red lines floating out into space. That's a shame, because that actually would make life a lot easier for hydraulic engineers. But if we could visualize it, it's shown here in this drawing as this red line labeled energy grade line. And by definition, the energy grade line is the locus of all the points of total hydraulic energy, including elevation, pressure, and velocity head. And then one last line here is this green line. Goes by a variety of names, none of which I'm sure are systematically uniform. I'm calling it bottom grade line because I'm not very original. Sometimes it's called the flow line. Sometimes it's called the profile grade line, but those are all pretty context specific. In any event, wherever the bottom is, we can keep track of that location. And if there were a need to draw a line to represent it, we could call it the bottom grade line. And it represents the topographic path that the lowest point in the channel of each section has. And that path also goes by the name of Thalweg, which is a German word for valley way. It's the way the valley travels. So if you see the word Thalweg in your literature, now you know where it came from. And as I stated a little bit earlier, if there were no head loss in the system, the energy grade line would be this horizontal red dashed line. But because there is head loss proportional to the friction slope, it's this line here, and the amount of head loss is the distance from the horizontal line to the energy grade line. In the picture on the right is a print from around the French Revolution illustrating that not only do open channels experience head loss, but aristocrats at the hands of peasants also experience head loss. And in this case, actually, they haven't lost the head, but the body's lost the head. So this kind of head loss is not what we're talking about, but now that you've seen the photo and heard my grisly description, you'll never forget the term head loss. And many years from now, maybe you'll associate it with this guillotine, but in fact, we're really trying to deal with the slope of the energy grade line. So if we were in a live face-to-face class, that would actually be funny, and we'd all be chuckling now. I wanted to leave that in. So uniform flow, by definition, is flow that occurs when the two flow depths, in the case of the previous drawing, y1 and y2 are the same. And in that situation, the friction slope, S sub f, would be the same as the bottom slope, S sub 0. And so that equation's written S sub f equals S naught, right there in the little white box in the center of the figure. And in fact, that equality is the definition of uniform flow. It also goes by the name of normal flow. Another type of flow regime for steady flow, or actually for unsteady for that matter, is called gradually varied flow. Gradually varied flow means that the change in flow depth, the y1 and y2 are now no longer equal to one another, but they change value over relatively large distances. The change is gradual, and that's called gradually varied flow. If we have an instance where y1 and y2 change quite a bit, and their spacing is pretty small, so maybe dozens of feet, that would be an instance of rapidly varied flow. And by definition, rapidly varied flow means that the change in flow depth occurs over a very short distance. So examples of rapidly varied flow that you've all already seen were in the hydraulic lab, where one of the lab exercises, they produce a hydraulic jump, or they produce flow through an energy dissipator, or they produce flow out of a sluice gate. Those are all examples of rapidly varied flow situation. That's outside the scope of this class, and in general, we probably don't want rapidly varied flow in our stormwater system very often. It's going to occur at inlets, that's unavoidable. But we usually don't want hydraulic jumps occurring within our storm sewer system. So the design concepts for open channels are, at high level, pretty straightforward. We would estimate the required system capacity for our study area, and that estimate will usually involve some kind of hydrology. So we're going to make some kind of estimation of what the rainfall runoff behavior is, and then we are going to attempt to accommodate that flow rate with our drainage system to protect infrastructure and prevent nuisance flooding. In the case of sanitary sewers, we usually estimate the discharge required based on the number of anticipated service connections. So sanitary sewers is somewhat easier. You count all the kidneys and colons and multiply it by a colon factor, and that gives you the required discharge. The second step after that's done would be we would use a uniform flow assumption, essentially what we just discussed, in order to size the conduits with adequate freeboard. Either the freeboard's indicated in the guidance documents, or we make an educated guess on what should be enough, because we don't want our channels flowing just about to go out of bank. That's actually bad engineering design. And then select slopes and hopefully achieve design velocities. At that point, we would perhaps adjust the design until the uniform flow velocities are satisfactory. Then we would evaluate the design using some kind of formal hydraulic model. Now, admittedly, the uniform flow is a hydraulic model, but by hydraulic model, I mean something that can capture the backwater effects and the effects of changing slopes and sizes and generate water surface profiles for us. And we use those water surface profiles to make the determination if the drainage system is containing the water at an elevation that we want, or if the water is having to come out of channel and suggesting that we need to make a change. So we can use the hydraulic model to adjust the design a little bit until we can get a hydraulically adequate design. Then generally we would check that the other non-negotiable constraints are satisfied. Do we have adequate alignments? Are we building the system in the actual right-of-way? Have we produced the system with proper setbacks from other systems? Stormwater systems and sanitary sewer systems have mandated setbacks from water distribution systems and other underground utilities. And so when we get to detailed design, we have to check that what we're proposing doesn't encroach on the existing underground facilities. And if it does, we move it a little bit, and if it's financially inconvenient to move, there are some fairly exotic materials that can be employed to allow encroachment into other underground utilities, but they're really expensive, so we only do them when we have to. And then we would iterate between steps 3 and 4 until you have a collection of workable alternatives, maybe just one. Estimate the cost, present that to the client, and then presumably we would proceed forward with detailed design, and that's the open channel design process. Those 5 steps are obviously hiding a lot of work. So the hydraulics of conduits requires the knowledge of depth area, depth perimeter, and depth top width relationships at a cross section. And so let's take a look at those coming up shortly on the guitar. Regardless of the section type, whether it's a semicircular section, a flat elliptical section, some sort of natural cross section, something that's kind of a trapezoid, somewhere between the two, the depth geometry relationships are all based on the same common theme. Basically, the theme is determine the depth area value, determine depth perimeter, determine depth top width. So let's look at what's meant by depth. So this drawing shows a arbitrary cross section, kind of trapezoidal looking, but a little bit curvy. So whether something like that would exist in nature or could be built and would be stable is a different story. But let's say that this exists somewhere. And we find the lowest spot in the channel, and the connection of all those lowest spots is called the Thalweg, and that's where we're going to measure depth at that point from. And so the channel depth in this drawing is measured from this location here and we're using the symbol Y to indicate how deep the water is in the channel. At the top of the Y, we have a free surface which extends from left to right bank in this drawing. And that distance, the point of contact from left to right bank perpendicular to the flow direction, is called the top width. Usual symbol is T for top width because T is the first letter of the word top width. Hence we use T. That probably actually is why it's a T. I've occasionally seen them use a different letter, and I won't relate the letter because I don't want to confuse you. But usually capital T is the top width when we're talking about open channel. T is also used for temperature and time, so it can be extra confusing. And if you can visualize a very thin additional layer of water that we can somehow put into this channel that is dy units tall in the depth direction, so maybe an inch tall, and T units wide, so it's at the top width wide, that little sliver of water creates an equivalent area, which we've labeled here as dA for differential area, and not da, which would be what Homer Simpson would. Actually, he'd use do. So anyway, dA, differential area. And that can be used to write the formal definition of what's meant by cross-sectional area. Now, nobody ever actually evaluates it using these integrals, but the calculus of it is that the area as a function of depth is the integral as tau goes from 0, the lowest point, up to the value of y, the current depth, of the top width function with respect to tau, d tau. So dA is equal to dy times t of y, and we're just putting that in the integral and then integrating from the bottom to the free surface. Similarly, there's a hydraulic variable called the wetted perimeter, and what it represents is the length of the water-solid contact. So in this drawing, starting here on the left side of the figure, and we follow the bottom of the channel till we get up here to the right side, and the red line that's apparent in the figure is the point of contact between liquid and solid phase, and the length of that line is called the wetted perimeter. Let's look at these terms in the rectangular conduit. And the top width is still the distance from left to right. The simplest geometry we can imagine is the mighty rectangle. And it's actually a legitimately useful geometry. Box culverts, which are common engineering tools in drainage that have a free surface, are rectangular. Rectangular channels are common in urban drainage systems. A rectangular channel will have to be lined. It's going to have to be concrete lined because a soil-lined rectangular channel would be nearly impossible to maintain. It wouldn't be stable. It would wash away. But having said that, box culverts and rectangular channels are very common engineering features in urban areas and in rural areas for that matter. So here's a picture of the mighty rectangle. So I have this black outline that just represents a rectangular cross section, and in this case the liquid is at depth y, indicated with the red line segment, and the area we're interested in is the blue shaded area. And pretty much by now, given that you've been in engineering for a while, you know that the area of that is t times y, or b times y. And so we could write the area of the rectangle is equal to b times y. The top width, as long as the water depth is non-zero, the top width is simply the width of the channel, capital B in this case. So t of y is equal to b. And in the top width of 0, would be 0. There's a discontinuity there. But once the flow depth gets down to 0, we're really not worried about stuff anyway. And then the wetted perimeter is simply this bottom width plus 1y up the right side plus another y up the left side, which gives us a wetted perimeter of B plus 2y. The last term that's important is a derived hydraulic property called the hydraulic radius, and it's defined as the ratio of the cross-sectional area of flow to the wetted perimeter. And essentially it's a concept so that we can apply the hydraulic equations regardless of geometry. Or another way to think of it is it's a characteristic radius that allows us equivalent comparison between a trapezoidal channel, a rectangular channel, a semicircular channel, parabolic, and so forth. For rectangular geometry, we actually can wrap our brains around the arithmetic. So the hydraulic radius is B times y divided by B plus 2y. So let's look at, do one thought experiment here. If the channel is pretty wide compared to the depth, suppose B is 100 feet and y is 2 feet. In the denominator, we would have 100 feet plus 2 times 2 would be 104 in the denominator. That's practically 100. So we could neglect the 2y in the denominator and find out that the hydraulic radius is approximately equal to by divided by b. Cancel the b's. The hydraulic radius is approximately equal to the flow depth for very wide channels. Keep that in mind, for very wide channels. So the flow depth of the Mississippi River is a very wide channel. In some parts it's well over a mile wide. And it's not particularly deep. I mean, it's too deep to try to hold your breath and swim along the bottom. But it's not particularly deep compared to a mile wide. 5,000 feet wide, 35 feet deep, that's a wide channel. And so the flow depth in the Mississippi River is a reasonable approximation of the hydraulic radius in many parts of the river. And that's a useful approximation to stash in the back of your head somewhere, because that may come in handy someday.
So you were saying when it's really wide, we can neglect that 2y term?
Well, think of it. If b is a big number and y is a little number, b is a big number, y is a little number, 2y is still pretty little. So b plus 2y is approximately equal to b, and the b's will cancel. You get a hydraulic radius equal to the flow depth. So for really wide channels, the flow depth and the hydraulic radius are almost the same value. But I'm not suggesting that you memorize it like that, but keep that approximation stashed away in the back of your head. The next geometry we want to look at is trapezoidal. And here is a picture of a trapezoidal channel. And this is a pretty common geometry, and interestingly enough, rectangular channel is a special case of a trapezoidal channel, and a triangular channel is also a special case of a trapezoidal channel. Most engineered natural channels or engineered concrete line channels are pretty well approximated by trapezoids, and so we can use that geometry to our advantage in a lot of different cases. The cross-sectional area flow is the same thing, the shaded blue area, as before. And if you take a look at this, you can see that there is a rectangle right there between the bottom width of the channel, and then we have these two triangular portions off to each side. And so to get the cross-sectional flow area, we take the rectangular portion, the b times y, and then we add the area of the two triangles. And in that case, the result is that the area as a function of y is equal to y times the quantity b plus my, where m is the horizontal portion of the side slope for each 1 unit of rise. I've written these equations as if the side slope on either side is the same. That doesn't have to be the case, and you would modify the requisite arithmetic in those instances. The top width is simply the bottom width plus the length of this leg on the triangle on the left plus the length of this leg on the triangle on the right, and that works out to be b plus 2 times m times y. The wetted perimeter is a little more difficult because we need to figure out the length of this hypotenuse with respect to the depth y, and we find the length of this hypotenuse on the left side also with respect to y. Add to that b, the bottom width, and that'll give us the wetted perimeter. So for this drawing, the wetted perimeter is b plus 2y multiplied by the square root of 1 plus m squared. And again, if you have different side slopes on either side, then this term gets broken into the two hypotenuses. Lastly, the hydraulic radius is the area y times b plus my divided by the wetted perimeter b plus 2y root 1 plus m squared. And there's no point in trying to reduce this any further. I would argue that you can't really make it that much simpler, and you don't have to, because as a practical matter, we would simply evaluate the numerator and the denominator, compute the ratio, and use that as hydraulic radius. So we can do that on our hand calculator, or we can code it up into a spreadsheet. In the case of this particular one, there's also an online tool, and let's go take a visit of that. Oh, it keeps going to the wrong toolkit. I gotta fix that. So be sure that the toolkit you go to is the one on Atomic Kitty, because that one actually works. The other one won't work right. And we'll go into the open channel hydraulics, and we have a trapezoidal channel hydraulic characteristics for US customary units. And you can use it for SI units, but you'll have to convert those yourself. And so if we were to enter a bottom width, I'll enter these numbers. I mean, I should get the same answers back. 5663. So if we enter a bottom width of 5 feet, the left side slope is 6 to 1. Right side slope is also 6 to 1. And let us suppose that the water's flowing 3 feet deep in the channel. It will compute the bottom width and regurgitate back left and right side slope, flow depth. It'll tell us what the top width of the water is. In this example, 41 feet. It'll compute the wetted perimeter, compute the flow area, and hydraulic radius. And so with this picture here, we would have all the information we need to apply a Manning's equation to this channel. And let me go ahead and leave that up. Let me get one more instance running. I often forget to put in the second. So I have purpose for doing what I'm doing right now. So we just ran this example. And so this has been reasonably well tested for a lot of different trapezoidal channels, and it gives you the ability to handle different side slopes. And it also has the equations that are being implemented. So you can use that to check any work that you do. To do a rectangular conduit, we turn the side slopes to 0. So we'll do the same input information, except now the side slopes are 0. Now this I can usually calculate in my head. The cross-sectional flow area is going to be 15 square feet. The wetted perimeter is going to be 11 feet. The hydraulic radius will be 15 over 11, which is about 1.4, something like that. So we do it, and we get the wetted perimeter 11 feet, flow area 15, hydraulic radius, I said about 1.4, 1.36. So the trapezoidal thing can be used for both rectangular and trapezoids. And then on the off chance we have a true triangle, let's just do a 6-to-1 triangle. Make the bottom width 0. It's moving that point and that point together, and so what's left is a triangle. And top width of 36 feet, wetted perimeter 21 feet, flow area 54 feet, hydraulic radius 2.5 feet. So to carry 3 feet of water in a triangular channel that has 6-to-1 side slope, we have to use 36 feet of right-of-way. To do the same thing in a trapezoidal channel that has some bottom width, we can use less right-of-way. So that's why the trapezoidal channel is in common use in practice. Our next geometry is the mighty circle, and it's obviously common in sewer systems. Pipes that flow with a free surface that happen to have circular cross sections are open channels. And it's an open channel until the liquid hits the top of the pipe, in which case it then becomes a surcharged or pipe under pressure. So using my drawing here, we have the water flowing at some depth y, and we're trying to find the hydraulic properties of this shaded area. One of the useful things we know is that because it's a circle, we know where its centroid is. Centroid is located at d/2 units from the bottom, where d is the diameter, and we know that a line going from the centroid out to the edge of the circle is a radius. It has length of d/2. So we know the length of these two arrows, and we can compute the angle between the vertical bisector and one of these radial rays that goes to the contact point where the liquid and solid are. And I've labeled that angle alpha, because alpha looks like a fish, and this is a sewer with water in it, and the fish want to swim in the sewer. And we're going to look for the top width and flow area and wetted perimeter with that information. So depending on the textbook that you get your formulas from, or if you do it yourself using trigonometry, the sweep angle definition makes a difference. So I've used alpha as the angle from the vertical bisector to the ray, but you'll see a lot of other books where they actually go from radius to radius. And compared to my drawing, that makes the angle 2 alpha. Once we've drawn the sketch, we can apply principles of trigonometry to find the value of alpha at a prescribed depth y, and it happens to be the arc cosine of the quantity 1 minus 2y divided by the diameter, where the value alpha is going to be in radians. And then once we have the angle, the area is straightforward. The area of a sector is d squared over 4 multiplied by the quantity alpha minus sine alpha cosine alpha. The top width for circular as a function of y is simply d times the sine of alpha. The wetted perimeter is d alpha, and the hydraulic radius is the ratio of area to wetted perimeter, and there is no benefit in attempting to cancel terms and simplify this equation. It's easy enough just to use it just like this. So calculate alpha, and you can calculate everything else. And then if you really hate calculating alpha, for every place there's an alpha, you can just substitute the arc cosine of 1 minus 2y over d, stick it in these different trigonometric functions, you get the same result. So this one was one that was over the years I thought was enough of a nuisance that it was worth building a online calculator to do it, and so we'll go do it. We're going to take a case where the diameter of the pipe is 6 feet, and we'll assume we have 5 feet deep of flow in it. So we go to open channel hydraulics, circular conduit, U.S. customary units. Actually, this doesn't matter what the units are. I suppose you could do meters and meters. But let's suppose it's a 6-foot diameter pipe, and we have 5 feet of flow depth in it. Go ahead and let it do its computations, and we get the computed angle, the top width, the wetted perimeter, flow area, hydraulic radius, and let's make a quick check. If the pipe is full, what's the angle going to be? It's either going to be a cake, or 2 cakes, or a cake over 2. The angle is going to be half a circle. It's going to be pi. It's going to be half a circle. So we get something around 3.1415976 and some change, 3.14159. So our algorithm seems to work for the pipe going full. And let's go ahead and make the flow depth 2 deep. So there's no error checking in the script, and if we do that, we'll get an internal server error. That usually means you entered the data wrong. So if the pipe is quite a bit not full, maybe it's flowing 1 feet deep, this is where the tool comes in handy. That would be a pain in the neck to do by hand. But we have the angle, top width, wetted perimeter, flow area, radius. We're good to go. We can use things like this to produce sketches, or what I call depth area diagrams, and those are usually quite a bit, quite handy, and we can put them in non-dimensional form so that we can dimensionalize to any size geometric structure that we've drawn a diagram for. The circular conduit is sometimes a nuisance to deal with the hydraulic elements, and that's why we have the online calculator. We can also build the calculators in spreadsheets, and we'll go take a look at one of those. We'll use the U.S. customary one. And we'll use the same values that were there. This particular one actually does the Manning's calculation for flow. So it's got a little bit extra that I haven't talked about yet, but I will in a few minutes. So the flow depth, I think we did before, was 5 feet. Diameter is 6. And it calculates the various terms and actually applies Manning's equation for us. So that's for circular flow. Circular pipe. And there's also a tabular version. We'll go look at that in a minute. There's a computation sheet for doing it with a hand calculator on the off chance that you don't have access to a computer and your phone can't reach out and touch the internet. So let's go take a look at that. You can build these on your own for any geometry you're using commonly. So we'll do the circular, and it's literally just like doing your income tax. Put in Manning's in, flow depth, conduit diameter, longitudinal slope. Once you have that, you can compute the ratio of depth to diameter. So you take line 2, you divide it by line 3, you put that value right here. Then you compute the cosine of alpha by this formula. Then you compute the inverse cosine of alpha by taking the inverse cosine of line 6. Then you compute the flow area by the area formula, weighted perimeter, hydraulic radius, transfer stuff from the prior page, and boom, when you get done, you have flow in cubic feet per second. And this is often overkill, but I suppose it has the advantage that it documents all your steps. And if you're doing a one-of calculation, and this would save you from having to refresh your hydraulics every time. You can just fill out the sheet. All it is an interface to calculations, which is no different than an online calculator, except it works. All you need for it is a table of trigonometric functions, the ID10T sheet, and a flashlight if you want to use it at night. The third approach would be to use a dimensionless chart, which relates full pipe behavior, because when the pipe is full, those geometric properties are fairly easy to calculate. The cross-sectional area flow is pi d squared over 4. The hydraulic radius is d over 4. And we can apply them directly in Manning's equation. And if we have a dimensionless chart that relates partial to full behavior, then we can calculate the discharge for any fill depth. So all those three calculators depend on this equation. Manning's equation, in general, is shown here. Q is 1.49 over n, A, r to the 2/3 power, s to the 1/2 power, where s is supposed to be friction slope, but a lot of times it's the bottom slope. And so a lot of times we are assuming normal flow in order to apply this equation. And the spreadsheet calculator I already showed you. If you're clever, you actually can highlight the various parts of the spreadsheet. And we have an online calculator available for direct application of Manning's equation. So let me go ahead and let's use the trapezoidal channel, but we want to use the 5663. I think that's the ones we want to use. 569 square feet. Well, we'll use this one anyway. So we have this slope area tool. If we have done the hydraulic calculator, in this case trapezoidal channel, and we want to determine discharge, we can use the slope area calculator, and we would simply supply the flow area. It needs to know that. Choose copy, paste. We would supply the hydraulic radius. Actually, I'll just go for the whole thing. Copy. Oh, made a mistake. Weighted perimeter. Copy. Paste. And then we would need Manning's end, so we could go look it up in one of these tables. Let's use 0.012 because I'm lazy. Manning's end. And then we have to supply the value of dimensionless slope, that S term that is in the equation. So let's do 5 parts in 1,000. So that's about 0.5% slope. Run the query, and it says we'll get 12,000 cubic feet per second. Hydraulic radius is 2.6 feet. We can check that, and sure enough, that's the correct hydraulic radius. Mean section velocity of 16 feet. That's a bit high for a trapezoidal channel, but not out of reason. We would probably jack with the slope and some of the other properties to We kind of want to get that down around 10. In the chat box it said, you said alpha is in radians. Yes, I did say alpha is in radians. It doesn't work very good if you do it in degrees, as I have it written. You could build the conversions in if you wanted. So there's our online calculator. We've seen the ID10T sheet for circular and SI, and then dimensionless diagrams is the last thing I'm going to talk about in normal flow. Using the same principles as the circular flow calculator, or any of the calculators for that matter, a dimensionless depth discharge diagram table can be constructed. And the way this is done is we're going to divide the depth into specific ratios of the diameter. So let's say a pipe is 6 feet in diameter. We will make a calculation as if the flow depth was a quarter foot, half a foot, 3/4 foot, 1 foot, and so on, and keep track of those depth ratios, and also keep track of the computed flows relative to the full flowing pipe. In forward computation, there's really no advantage. But if you have the tabulation of the dimensionless chart, it's really handy for doing the reverse lookup. So let's go take a look at one of these. Yeah, I'll do it here. Good, it's got the dimensionless chart here. And what we have is a table. We copy Manning's end, diameter, and dimensionless slope. So this is basically employing Manning's equation. And we make the flow depth a certain fraction of the total diameter. And once we've done that, we can compute a ratio of flow depth to total diameter. So the ratio is showing here, going from 0.05 all the way down to 1. Then we apply the individual equations for each row: angle, flow area, wetted perimeter, hydraulic radius, Manning's equation to produce the discharge. Then we take the discharge in this first row, divide it by the discharge in the last row, which corresponds to a full pipe, and tabulate those dimensionless discharge ratios. And plotted it.
See your mouse moving, but it's still on the Atomic Kitty website.
Okay. Oh, you didn't see any other spreadsheets then, did you? Oh, that's embarrassing. There we go. I'll go back and visit the other spreadsheets shortly. Thank you for telling me that, because I would have just proceeded blindly along. So let's see what I said before. We have pipe diameter, which can be variable. We compute flow depths as a fraction of the pipe diameter and record that. So this column right here is plotted on the vertical axis on this chart, and the discharge ratio, right? You're just not going to work today, are you? There you go. The discharge ratio right there is plotted on the horizontal axis. And it's a dimensionless chart, so if I change the pipe diameter, the picture doesn't change. If I change Manning's end, the picture doesn't change. If I change the slope, the picture doesn't change. But you notice all the table values changed. And so the beauty of a dimensionless chart is the two things that we're plotting stay constant regardless of the other components. And we can always calculate this last line pretty easily, because that's just Manning's equation for the pipe that's full. So we know the area and we know the hydraulic radius. And so from the chart, we have a plot of discharge ratio on the horizontal axis and depth ratio on the vertical axis. And we see an interesting thing here that actually the highest discharge occurs at about 95% full, and then it goes back to the one-to-one match. And what's going on there in real world is actually there's an air bubble that's progressively burping in the pipe, so it fills up, slaps out the air, and gets a little bit of extra acceleration and can carry more discharge. We would never try to operate a system right at this location, but the nice thing it does is it guarantees us this amount of freeboard in any initial design that we make. There's always a little extra capacity when we use circular pipes. So the way to use this, not in the forward direction, but in the reverse direction, is if we had a specific discharge we wanted to accommodate, and we wanted to accommodate it at a particular flow ratio, we could work this chart backwards, find what the depth diameter ratio is, and use that to select an appropriate diameter. And we'll do that not today. We'll do that in a future lesson. Okay, so the other charts I showed earlier that you all saw the mouse moving, but you didn't see a chart, was this one. This one is just a direct entry for computing the intermediate computations as well as discharge and velocity. And there's a few others along the same genre. Let's see, partial full, circular, SI. Yeah, this one has the colorful input. So these are sitting on the web server, and there's no great magic to it. It's just implementing Manning's formula under either SI or US customary conditions. And recall from your hydrology class that Manning's formula changes whether you're using US customary or not. How come it won't let me exit? Don't force me to reboot the computer. All right. So we visited this spreadsheet already, and we produced this dimensionless diagram. And here's how to use it. For the forward calculation, we would determine what full pipe discharge is, and there's the formula for full pipe discharge. That's reasonably easy to remember or fabricate from first principles, because this term here is the cross-sectional flow area. This term is the hydraulic radius, and usually the value of S is the bottom slope. And so we would determine the flow depth ratio of interest. So suppose we want to operate the thing at 3/4 full, then the flow ratio is 0.75, and we would use the chart to find out what the dimensionless discharge is for a fill depth of 0.75. So somewhere over 92, I think, from 0.911. So 91% for 75% full, and then we multiply that discharge fraction by the computed value for Q full. So Q at 75% fill depth is 0.91 times the discharge at full depth. And you'll see these dimensionless charts in other places. Here's an example of one that's taken from the NCEES supplied reference, which is the tool you'll use when you take the FE exam. And the spreadsheet calculation essentially produces this red colored line. In this particular chart, they're plotting a whole bunch of stuff, in theory to make efficient use of the chart, but in practice to confuse the heck out of anybody that has to use it. You have to read these pretty carefully to find out what each dashed line is, and you have to find out what they're pointing to, that these are velocity lines, and then there's a hydraulic radius line, and this is the discharge line that we've been looking at. The value of these charts comes when doing a reverse lookup, when going backwards, when our goal is to select a design diameter for a required fill depth and a supplied discharge. And that's a pretty realistic need because many of our guidance documents will stipulate that large diameter sewer can be run at 75% full, small diameter sewer at 50% full, and once you know that it's going to be at 50% or 75% full, then you would determine your design discharge that conduit needs to carry, and you can use one of these charts backwards to determine the required diameter to accommodate that flow at that prescribed fill depth. There's also dimensionless charts for trapezoidal channels, and here's an example from FHWA HEC 22, and it has a description on how to use the chart. We have to specify channel width, side slope, longitudinal slope, material properties, and discharge. We locate the value of longitudinal slope on the chart. Then we compute the product of discharge times Manning's end. Find that point. We join those 2 points with a line. That's what this dashed line is here, until it hits this line labeled the turning line. Then we locate the bottom width value on this scale, and we draw a line from the turning line intersection through the bottom width line until it hits this depth over bottom width graphic, and then we move horizontally depending on what the side slope is, and from that we can read off a particular value of the flow depth to bottom width ratio, and because we know the value of bottom width, we can multiply off of this chart the bottom width to recover the actual flow depth. So that's nowadays that probably seems kind of silly, but this was the state-of-the-art computational tool not that long ago, and it's essentially a graphical solution to what we can accomplish with a web calculator now. So, okay, that was all I had for today. I want to thank you for mentioning that you could see the mouse moving, but you couldn't see the spreadsheets. And in the future, when I do that again, because I probably will, go ahead and pipe in right away. Don't let me move around and not see what's going on.
You got it.
Because that's kind of meaningless. And let's see, in the chat box, there was a comment from Stephen, who said, and you said alpha is in radians, and I said, yes, it is. Let's go back to the section that it's relevant. I'm not going to prove it to you, but I'm going to just state that. So in this analysis, in these particular trigonometric functions, alpha is supplied in radians. And same thing in the actual computational tool. I have no comment on that. If you only have it in degrees for some reason, if you divide the number of degrees by 180, that should give you the angle in radians. Let's see if I got that right. 2 pi is 3, so yeah, 180. The angle in degrees divided by 180 would be the angle in radians. And then you could apply it directly into these formulas as is. Alternatively, if you're into programming, I suppose you can program this to accept values in degrees. But the beauty of it is that we actually don't care what alpha is. We just need to calculate it to use the other formulas. So by all means, feel free to use the online tool. I'm confident that it works correctly. So with that, I will end the screen share, and I will terminate the call and render the video and upload it. Are there any other questions, or shall we call it a night? Okay, well, thank you very much for your attention. Man, it's getting dark early now, so it must be getting to be fall. And have a great evening. Have a good day tomorrow, and I will see you again on Thursday evening. So take care. Remember, you have an exam that's due tomorrow, so work on it tomorrow sometime.